just want to try working through a PChem problem here about basically a monoatomic ideal gas that is expanding adiabatically. All right, so when we're talking about adiabatic expansion, we know that Q equals 0. This is essentially pretty characteristic of this sort of system. When you essentially compress an adiabatic system, it's going to be isolated from the surroundings, meaning there's no transfer of heat and there's no transfer of material or of matter at all. So this is going to be very, very important in determining how to do this problem. Other than that, because of this relationship, we know that U equals delta U equals delta W. So your internal energy is just going to equal your work in this scenario. All right, so we're given P1, we're given T1, and we're given P2. So in this sort of case, we do need the temperature values, as we have some equations that will help us solve if we have both the final and initial temperature. So let's try getting the temperature 2 value. All right, so to receive temperature 2, we have to use this equation that I have here, T2 over T1 equals P2 over P1. And then right here, it's Cp over Cv minus 1 divided by Cp over Cv. All right. So now that we have this equation, we can start plugging in numbers. So for a monatomic gas, our Cp value is going to be, Cp for monatomic is going to be 5 over 2R. Our Cv is going to equal 3 over 2R. All right. So let's start plugging in numbers. So we want to isolate for T2 here, which is one value that we are not given in this equation. So T2 equals T1, P2 over P1, Cp over Cv minus 1 divided by Cp over Cv. All right. So let's start plugging in numbers. We have T2 equals, our T1 value is going to be 300 times, P1 is that value, P2 is that value, so 1 over 1.9494 to the power of, our Cp is going to be 5 over 2 times R over 3 over 2 times R divided by, oh, I forgot the minus 1, and that's divided by 5 over 2 times R over 3 over 2 times R. All right, let's do a little bit of number crunching here. These R's cancel. Once again, these R's cancel as well. In this sort of case, we can flip the fractions and multiply. So we have 5 over 2 times 2 over 3 equals 10 over 6. So 10 over 6 minus 1 equals 4 over 6. Cool. And then we have 5 over 2 over times 2 over 3. But this time we're dividing. So 4 over 6 times 6 over 10. Do some reducing here. 5. This is 1. This is 1. So we end up with this fraction of 2 over 5. And that should equal 0.4 as well. So we have 300 times times 1.1 over 1.94 to the power of 0.4. And then doing a little bit of math in my calculator, I get the value of 300 times 1 divided by 1.94 to power 0.4. This is 230.14 Kelvin. And that's going to equal our T2 value. Perfect. All right, so let's continue on solving this problem now. So let's see which ones we already have. So we know that the heat Q equals 0, right? So that's one of them that we already have. We also know that delta S equals Q reverse over temperature, right? So our Q reversible here is 0, so this also equals 0. So we've done that, and we've calculated the heat. Now let's calculate the work, the internal energy, and the enthalpy. All right. As you can see here, the internal energy equals the work, so we can also just recycle that as well. All right, so first let's try to basically solve for the internal energy. So I have another equation here, delta U equals the integral of T2 over T1 CV T dt. All right. So this is going to be the equation that we use to solve for our internal energy as well as our work. So essentially delta U equals, and in this case CV is going to be a constant. So CV with T2 minus T1. Crunching these numbers out, and in this case CV is that same value that we had before. So it's delta U equals 3 over 2R times, our temperature 2 is about 230 minus 300. Crunching some numbers, I get the value of over 2 times 8.314, which is the R constant we're using in this case, times 230 minus 300. That equals minus 872.97 joules. And since we are in an adiabatic process, this also equals the work. So we can scroll up, and that is 2 birds hit with 1 stone. Oops, I just cross off work there. All right, so let's solve for delta H now. So delta H has a different equation that will be important to remember, especially if you're taking an exam. And this other equation is pretty similar, but it uses a different term. It uses the term CP. All right, so this is the term for this. And basically the integral is pretty similar because we assume that this is going to be constant. So we have delta H equals CP T2 minus T1. And then in this case, for a monatomic gas, we expect the CP value to be 5 over 2 R times T2 minus T1. So this is going to be 5 over 2 times 8.314 times 230 minus 300. All right. And the value that this spits out is 5 over 2 times 8.314 times 230 minus 300. And the value that this spits out is going to be minus 1454.95 joules. And this is going to equal your enthalpy value. Perfect. All right. I hope that you guys found this video helpful, and I hope you the best of luck, whether you are doing a PChem